In previous videos, we've talked about the history and the development of the finite element analysis methods. We've spent a great deal of time so far talking about the direct method, which requires an understanding of Hooke's law in order to develop that method, and the differential equations we're applying our problems to, or our method to, requires that Hooke's law apply to those situations. We've then went on, and in the last few videos, we've discussed and we developed methods based on the principle of minimum potential energy. These methods require some physical understanding of our problem in terms of the amount of potential energy stored in the system. We're not going to work with virtual work methods, but if we were to develop those methods in this class, in order to use those methods, we would need to have some understanding of the amount of work or virtual work that our system could perform and the amount of energy flowing through our system. In today's lecture, we're going to develop what's called Galerkin's method, which is one of these methods based on variational calculus, where there's no need to have a physical understanding of the differential equation we're trying to model or we're trying to solve in the development of our finite element analysis method. So let's spend a little bit of time talking about the different differential equations that we might want to deal with using the Galerkin's method. So I've drawn up here the type of one-dimensional bar element we've seen quite a bit in this class. In this particular bar element, I can see that I have some distributed traction load defined by t, which is a function of x, applied along the length of this bar, so that if I was to integrate over the length of the bar, I would get the force applied along the entire force applied along the length of the bar. Now, I have this force along the length of the bar. I could equally write that as, remember, force is the stress times area. And of course, the stress is just the strain times E times the area. And of course, we defined stress earlier as du dx and if I wanted to differentiate both sides, I would find a differential equation d dx of E a du dx is equal to tx, which is a differential equation that models the types of one-dimensional bar elements that we've been talking about so far this entire semester. But now let's look at a different problem. Suppose instead of a bar that's being stretched, suppose I had a bar of various temperatures, and rather than displacement, it's the temperature of the bar that I'm interested in. And let's say that I know the temperature at this point, we'll call T2, we'll call point 2, and I know the temperature at this point, we'll call T1. Maybe somewhere along the length of this bar, I'm also adding heat, which we'll call Q, which is a function of x. And I'm applying heat along the length of the bar. And what I'm really interested in is knowing is, OK, what is the temperature along the length of the bar as a function of x? This is a well-known physical problem. There's a differential equation for it that has been derived in a similar way that I derived this differential equation. Here, again, temperature. T is for temperature. A is cross-sectional area. Here, this kappa stands for the thermal conductivity, and Q is my heat supply. There are other differential equations, such as differential equations that involve a 1D electrical current and also 1D diffusion of some chemical, say chemical being diffused down a narrow river. Notice that all of these differential equations have similar form. There are also 2D and 3D forms of all of these differential equations. And all of these different types of differential equations can all be solved, or approximate solutions can be found using the methods that will be covered in this lecture. So how are we going to develop the Galerkin's method? Here's our plan. The first thing we're going to do is we're going to start with what's called a boundary value problem. That's a differential equation with boundary conditions. Either I know the values of the function I'm trying to solve for at the endpoints, or I know perhaps the derivatives, the values of the derivatives at the endpoints, or I know some combination of those two. Our next step is to convert this differential equation and boundary conditions, which is what's known as the strong form or the strong statement of our problem, into something called the weak form or the differential form. I'm sorry, the variational form of our problem. And we'll discuss this in more detail in the next video. Finally, our last step is once we've converted our strong boundary value problem into a weak variational problem, we will make certain approximations to this weak form using one of many of these variational finite element methods. We're going to focus on what's called the Galerkin method. If you're interested, your textbook goes into some other methods, such as the collocation method, subdomain method, or the least squares method. All right, in our next video, we will discuss converting a boundary value problem in the strong form and converting it into the weak form.